It's very powerful that I use prostheses myself, and on a few levels that's important. One is I intimately am aware of the consequence of poor design. I've spent my life trying to work with bad design, and I know firsthand how devastating and painful it is to trying to go about the world and you're surrounded by technology that's incredibly poor in its conception and design. So that's one aspect. Another aspect is I'm often the first human to test the technologies that are being conceived in my laboratory. I'm the first person to feel it, to experience it. Because I can feel it, and I also know the physics and engineering in my head, I can really quickly find the bug and solve the bug. Where another person may know the science and the engineering, but can't feel it, so doesn't come to the solution as quickly as I do. So that's an interesting advantage that I have. And regarding my passion, again, I know how painful it is to be in a world with design that doesn't work. And I know how extraordinary it is and life-changing it is to be given the gift of a fantastic design, whether it be a beautiful chair or a prosthesis or an exoskeleton. Great design leads to just absolute joy and human expression. So what really drives me and my passions and whatnot is the times in my life where I can put out into the world a fantastic design that improves people's lives.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwayne, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast. I'd like to go back when I think you started your career, and I think it's very inspirational for anyone listening to that. And I'm curious about when you started at age 17, is kind of rebirth happened to you to start thinking about new bodies, or what kind of question, what kind of thought at this moment to have rebirth as a new life?
When I was 17, I was in a mountain climbing accident and suffered frostbite to my lower legs. And after months of effort, my medical team had to amputate my legs due to the health risk of gangrene. After my legs were amputated, I wanted to return to my chosen sport of mountain climbing. So I designed and fabricated my own artificial limbs for the vertical world. So I had specialized limbs for standing on small rock edges the width of a coin. I had specialized limbs for climbing steep ice walls and so on. And from this body hacking, if you will, I was actually able to climb at a more advanced level about a year after my legs were amputated than I had achieved before the accident with biological limbs. So this was very inspiring, and it led me to my current research objective of human augmentation.
Mm-hmm. Actually, I admire being creative and having kind of being not fearless about maybe what society or at this time. I'm curious about this kind of motivation and inspiration to design your own artificial limb. How do you start design and thinking about something and having a challenge to design something for at the time was kind of not intelligent or doesn't have any capabilities. So starting from simple things to design your artificial limb, how did you start think about that from simple material at this time?
Yeah, you're correct. I at the time I didn't have many resources, and I wasn't educated in engineering and design. But I was familiar with machining. I spent my high school in a machining curricula. So I did know my way around a shop, and using passive materials, I fabricated feet. I optimized their geometry, their impedance, their compliance for these various extreme conditions of ice and rock climbing. And it worked remarkably well. As I stated, I could climb more difficult faces than I could achieve before the accident. And that, from that experience, I realized that technology has the power to heal, to rehabilitate, and in my own case, the authority to augment human capability. And that inspired me to go back to school and study science and engineering and design.
Mm-hmm, mm-hmm. How do you see this kind of embodied, as we speak about how the brain and the body work, for you, how you define the relationship between the brain and the body, and especially if we imagine new bodies, not exactly as we see at the human. And I think that's really beautiful, that how you define the beauty and the shape of the human. If you can tell us about your vision about this kind of a change, how you see the relationship, shouldn't necessarily the human body be the same shape all the time, the design, the way you think about it, because you clearly think it's not all necessarily you have the same biological shape of the human or the same, maybe, I don't know how to call it, but same morphology maybe. So for you, how do you see this relationship here? Your philosophy about that?
Yeah, Bionics, the field of Bionics, human Bionics, seeks to develop synthetic and biological constructs that in the end emulate an anthropomorphic or normal biological morphology and dynamics. But of course, augmentation is broader than that objective. We can imagine non-anthropomorphic capabilities, humans with third arms, for example, or much greater vision or hearing capacity or thinking capacity. So an example of that is, early on, I adjusted the length of my legs or my stature well beyond that of a normal stature, to be able to reach hand and foot holds in a accelerated or augmented manner. So even in those early design days, I was exploring this idea of non-anthropomorphic augmentation. And I'm thinking broadly as we, march into this 21st century, I think that form of augmentation will become more and more paramount. And at the twilight years of this century, I predict that humans will be unrecognizable from what we are today, morphologically and dynamically. In my MIT lab, we're exploring connecting the human nervous system with synthetic computation bidirectionally. And when we do that, we achieve an embodiment where the human feels embodied into the designed construct, as if it's their flesh and bone. So that's very interesting because the design construct doesn't even have to look like a biological limb or body part. It can be perhaps wings or any type of form that potentially the nervous system could embody.
Mm-hmm. That's interesting. Before going to that, I'm curious if there's maybe people sometimes argue with, I think you mentioned that before about this kind of godly shape and morphology, and you designed something that can enhance or maybe beyond what we already have as a human, and that's clearly what happened to you. So do you think this kind of notion, people disagree that designing something that could surpass what we have already as a human or godly creature, as you call it?
Acceptance. I mean, already today we're surrounded by technology that augments human capability. Our smartphones, as an example, airplanes, automobiles, all these devices enable humans to do things they're not able to do with just their bodies. So, I mean, and we often don't view it as augmentation because it's ubiquitous and it's everywhere and we're just used to it. And so the future happens slowly. We slowly become more and more augmented. And because of that, that slow speed of augmentation rate, it's never really surprising, and we continually believe that we're not augmented, but we are in fact. So my lab was the first to develop a leg exoskeleton to augment human walking and running and jumping. And that type of technology of augmented humans through exoskeleton bionics, we're going to see commercially in just a few years, so it's very exciting.
Mm-hmm. And I'm curious about the struggles when you go through all these years about the design and how we approach designing different prosthetic for different purpose. What kind of struggle do you have in design and the way of thinking, how you optimize this design? If you can tell us more, what's the challenging part of all these years to design what we have now already adaptable to the movement as a human? What kind of struggle did you have all these years?
Yeah, it's very, very difficult. Us humans were very, very, very proficient at walking. We've been doing it for a very long time. So the idea of developing a machine that makes us even better at walking and running and jumping is an extraordinary task. Our primary strategy is to try to determine where humans are inefficient and where we are efficient. And where we're inefficient, using technologies in a very clever way to augment, to improve the efficiency. So for example, when skeletal muscles do positive thrusting work, they're very inefficient. The muscle gives off a lot of heat. So we look for walking and running gaits, we look for areas of the gait for which muscles are doing a lot of inefficient work. And then we replace that work with a motorized exoskeleton capability to effectively reduce the amount of food energy or metabolics used to move. So imagine a leg exoskeleton where one could run through the wilderness across rough terrain without even breathing hard and not being particularly in shape. When that's invented, no one will ever use a wheeled mountain bike ever again. If we capture both the versatility of human legs and we improve the efficiency or economy of movement through exoskeletons, it will be a remarkably fun toy.
You already have some already prototype, but what do you think may be missing to achieve this kind of, you want a human to be superhero, as you mentioned, so what's maybe missing, the overall picture?
Yeah, I mean, to really solve Bionics, there's a few areas of challenge. One is the mechanical interface between the Bionic synthetic device and the human body. How do you attach a device to the human skeleton or body in a comfortable manner? A second interface is neural. How do we connect the brain to Bionic devices? And the third, I suppose, is the capacity to build Bionic devices that move like us, which relates to power supplies and muscle-like actuators, if you will. So those three interfaces, the last being dynamic, the second I mentioned being neural or electrical, and the first being mechanical, those are the key challenges of physical augmentation Bionics.
Mm-hmm. And what could be still maybe for you can't understand about the human movement, whatever kind of locomotion, still maybe challenging for you to understand how you can make this connection between biology and bionics, or maybe later about cyborg. So what could be maybe still for you challenging understanding?
Yeah, to me, cyborg suggests a bidirectional connection between artificial computation and the biological brain. So in the case of a prosthesis, the human can think and affect, put information into the synthetic computer, and in turn the synthetic computer can insert energy back into the nervous system. So closing the loop creates the cyborg function. Yeah, what are the challenges? There's many challenges, but the dominant one we're working on is how to create that bidirectional link between small little computers and an interface to muscles and nerves in terms of information signaling. So we're looking at ways of connecting to nerves and muscles, novel surgical strategies, for example, novel implants into the peripheral to record these various signals.
Mm-hmm. And may I ask you, why do you think, for yourself, for example, the Bionic one and the cyborg, what should maybe you don't want to choose the later, for example, cyborg? What is maybe for you the option? I mean, why choose for Bionic, for example? If there's an advantage for being Bionic over cyborg in that case, or?
So Bionic is is perhaps a subset of cyborg function. So again, cyborg simply means that the brain is connected to the mechatronic device bidirectionally. Cyborg does not necessarily suggest that it's biological-like or human-like, which Bionic does, human Bionics does. So you can be Bionic but not a cyborg, and you can be a cyborg but not Bionic. So they're somewhat distinct, in my view.
Mm-hmm. But you don't think maybe there's advantage for using cyborg now?
Yeah, the bidirectional link to the brain, there's profound advantages. Our brains are remarkably adept. It's remarkable what we can do from a motor physical perspective. And from an exoskeleton prosthetic perspective, that cyborg bidirectionality is critical for embodiment. So if you want to give a person, for example, with limb amputation, the feeling that the synthetic limb is actually themselves, is part of their body, then I believe strongly that the bidirectional brain linkage is essential. So of course, we in the field could continue to advance robotics and AI and build purely intrinsic prosthetic limbs that are highly adaptive and emulate very closely biological dynamics. But the problem with that approach is that the human would never feel connected to the device and would never feel embodied. And it would feel like, as an analogy, that you would always be sitting in the back seat of the vehicle, but you'd never be the vehicle or your hands on the steering wheel. So it's very important to, as a field, that we pursue a high fidelity linkage between the human brain and synthetic computation elements that sit on the bionic structures. Because only through that will we seek embodiment, where a person with limb loss after going through bionic reconstruction will truly feel that they have their body back. That is the clinical goal.
Mm-hmm. And I'm curious to ask you, do you think the approach should be invasive or non-invasive? Which one do you think is more maybe reliable to the way of the communication between the brain? If we speak about bidirectional communication here, you already, I think the approach you try to use invasive ones. But do you think generally the invasive or non-invasive one more reliable for communication between the nerve and the prosthetic limb?
Well, the spectrum of non-invasive to highly invasive, there's an intermediate stage of minimally invasive. So the question is, across that spectrum, what are the advantages and disadvantages? Typically, purely non-invasive interfaces have a very poor signal quality, and they can also be uncomfortable. So there's a limit in comfort, there's a limit in how much you can extract from the signals that are collected with non-invasive electrodes, for example. The advantage of highly invasive is you get beautiful time-invariant signals, but it's invasive and may require surgeries and tremendous cost and whatnot. The minimally invasive point, intermediate point, is very interesting because it requires very minimal surgery, but you still can get sufficiently good signals in terms of quality. So that's in my lab at MIT, we're exploring minimally invasive neural interfaces to muscle, for example. Our approach is to implant small little spherical magnetic beads into muscle, and then we're able to, with external electronics outside the body, measure how the muscle moves dynamically with very high accuracy and precision.
Mm-hmm. And do you think for the material part as well, this kind of connection between, as you mentioned, you feel it's part of your body, and that's wonderful feeling that it doesn't matter if it's like biological part or synthetic part, but do you think the material so far, how it's really playing a crucial role in this design? Do you think there's something should be investigated more, or advancement in the material part, this kind of artificial skin or this kind of connection in the materials?
So if we solve the linkage between the human nervous system and mechatronics, from the perspective of the human, it won't matter that their limb may be synthetic. If you completely maintain the signals coming out of the brain and into the brain, the central brain won't know what the limb's made out of. And we're already seeing this in our work. So in a sense, if you connect to the nervous system well enough, the brain won't even realize that the limb has been amputated and rebuilt with synthetic materials. Now, the assumption there is that we've completely maintained the information flow into the brain, and that requires fantastic sensing in the artificial construct that's biomimetic, and it requires a high bit rate information flow into the nervous system. So these are all tremendous challenges, and the material and the sensor design is, of course, very important for that goal.
Mm-hmm. And when you try to upgrade each version, what's actually looking for in the performance? If you could just deeper about the way you think about upgrading the design, or how do you think about approaching this kind of upgrading certain features, or this part should be improved? Which one do you go for? It's like the computational part or the mechanical design of the materials?
My lab at MIT is very, very diverse from an intellectual and skill set perspective. We're approaching the problem from most directions. It's perhaps one of the most diverse labs in the world in the area of bionics. So we're doing genetics, we're doing machine learning, motor design, power supply design, tissue engineering, across the board. We're integrating these formal disciplines and creating these bionic platforms. So the human body is very diverse. The human body is chemical, it's mechanical, it's electrical, and so on. So to hack the human body, intellectually, the team has to be very, very diverse, or that team will not be successful. In addition, beyond science and technology, the team also has to comprise designers and artists. If you're reimagining the human form. We want to also think about aesthetics and not just functionality.
Mm-hmm. If there's something this years was very challenging to design, and maybe not intuitive how I can design something like that, it was super challenging, and maybe ended with something very beautiful in the design.
Yeah, with artificial limb design, what we typically do is we design a limb that has the shape of a normal biological limb. But when you peel off the artificial skin, it doesn't look biological at all. And we do that because the human user of that limb can one day want to hide the fact that part of their body is artificial and will use that synthetic skin. And the very next day, they may have a different mood and want to go to an interesting party and celebrate the fact that part of their body is a machine and exhibits a machine-like beauty. So allowing the user to explore both a human beauty and a machine beauty from day to day is what we would like to see in terms of our design goals.
Mm-hmm. And when you see the intelligence in the design, do you think, for example, the reflexes that you mentioned before, how this kind of reflects in behavior or adapting to maybe uncertain scenario, how do you see the design between this bidirectional, for example, to adapt to uncertainty or maybe situations maybe not expected?
Well, I mean, the challenge of a purely intrinsic design where all the sensing and computation is on the synthetic device, the challenge of the unexpected banana peel on the floor is very, very difficult. If you link the brain bidirectionally to the synthetic limb, you essentially solve that problem to a degree to which the biological system's capable of adapting, capable of tremendous versatility. You tap into that intelligence and you, if you will, get it for free. So that's another reason why I think as a field, we first need to solve the interface with the brain. And once we do that, sure, we can use artificial intelligence to augment humans beyond natural capabilities. But first and foremost, we need a high fidelity linkage to the brain. The dominant challenge is the link between synthetics and biologics. So if you want to collect signals from a nerve, motor signals, to extract how the person wishes to move, and if you want to reflect the sensory information from the bionic appendage onto the nervous system, the actual connection to the nervous tissues is the challenge. But there's been tremendous progress in the last decade in that regard, and we're starting to see tremendous progress.
Mm-hmm. And being creative, I don't know how do you see that's kind of maybe what's next, or maybe what you want to see in the maybe the different bodies or new morphology. How do you see this kind of creativity in the design? Do you think being functionality or inventing new things? How do you see being creative in the design for what's next?
Yeah, our approach at MIT is I call neural embodied design. So most designers in Bionics, they think about the design of a synthetic device that somehow interfaces inside the body or is attached to the body. They don't think about fundamentally redesigning the body. So neural embodied design, we not only design synthetics, but we design the biological body. And we explore that interplay between biological design and synthetic design to try to maximize, again, the bidirectional communication between the brain and the device. So because of that, we invent surgeries. We invent new proteins to be able to turn on and off cells. All these areas where we don't view the body as invariant. We do view the body as an area for which one can design. And because of that philosophical difference, I believe we're seeing tremendous success in neural interfacing.
Mm-hmm. And I don't know if do you think about the future of the design of the prosthetics and exoskeleton. Where do you think maybe the advancement should be lies in the next generation for exoskeleton and prosthetics?
Yeah, so the word exoskeleton, my definition of that is a device that typically runs in parallel to a limb, your leg, for example, that comprises motors and structures to apply impedances and positions and torques on the body. And an exoskeleton is typically used for human augmentation, where an orthosis is used for medical purposes, for rehabilitation. So exoskeletons, again, that would be for augmentation. A lot of the same challenges exist between exoskeletons and medical prostheses. Again, there's the goal of how do you extract the intent of the human, how the human wishes to move? How do you insert information back into the nervous system to to give the human brain information about the state of the mechatronics and the biological body? How do you attach to the body mechanically? Building an exoskeleton that, touches us from the outside and exerts forces and torques is very hard because us humans, we're very soft. So you're pushing on soft tissue, and it's very hard to efficiently apply torques about the body with such a soft substrate. So all these are tremendous challenges. But just, my lab at MIT was the first, as I mentioned earlier, to build a leg exoskeleton that augments human walking and running. Believe it or not, that occurred in 2014. So for over a century, scientists and technologists have been trying to augment humans with exoskeletons and just experiencing failure after failure. It wasn't until 2014 that there was a success. So again, as I stated earlier, us humans are very good at walking. We're very good at moving. We've been doing it for a very long time. So to build a machine that makes us even more efficient or more economical is a tremendous feat.
Mm-hmm. And I'm curious, do you have any maybe surprising moments? I don't know, maybe through testing certain prototype over these years was surprising to you or unexpected. Do you have this moment, any moment like that's surprising or not expected, that work and that behavior or having that?
Yeah, I mean, most days as a researcher, most days are very frustrating, but there are some days that are magical. As I mentioned, my group invented a new way of amputating limbs called the Agonist, Antagonist, Mylenor interface, or AMI for short. And in the surgery, we dynamically link muscles to kind of create a biological joint within the amputated residuum. And then we link sensors to those dynamic muscle pairs to control the bionic limb. So when our first human patient, when we wired him up after his surgery, he quickly was able to control the bionic ankle and bionic subtalar joint. So he's moving his foot-ankle complex like this, his bionic foot-ankle complex. So we were excited about that because that in itself was novel. But then he stood up and he began traversing slopes and steps and various irregular terrain surfaces. And his synthetic limb was just adapting to the terrain as if his limbs were biological. And when we asked him, are you trying to move your limb in that way? And he says, no, I have no, it's involuntary. I'm not conscious of the movements at all. That was an extraordinary day in the lab, because we realized that if you give the brain natural proprioceptive signals, the human brain knows exactly how to control the synthetic limb as if it's a natural biological limb, without even the human being aware that the movements are happening. So that was a wonderful day.
That's great. I don't know if you have sometimes to become design, there is a trade-off, and you have been working now for, I think, over 30 years or more. There's kind of a trade-off, do you think, still very challenging to, you mentioned it's still the limitation, but what kind of the trade-off do you think is very hard to overcome this trade-off in the design?
It's my lab at MIT. The goal is to not only expand human knowledge, but also to ultimately develop technologies that humans can use to translate ideas into clinically viable technologies. And that's a very, very huge challenge to innovate. So that design matrix includes not only elements of functionality of the device or system, but also cost and manufacturability, whether the device can be reimbursed, whether the device has safety that it can get through the FDA, for example. So the complexity of building a bionic body part and actually translating it to society is just enormous. It typically takes me a decade to build, design, and launch a bionic body part, whether it's a foot or a knee or a hip or whatever. It typically takes me a decade to innovate. That's how hard it is. So there's many, many trade-offs that one has to make in that extraordinarily complex effort. What I mentioned earlier, that we have highly invasive interfaces to the brain and interfaces that are completely non-invasive, and then in between is minimally invasive. Minimally invasive is a beautiful trade-off because you've minimized the level of invasiveness. So yes, it requires a surgery, but it's on an outpatient basis. The regulatory hurdle is modest, the cost is modest, but still the signals have very high quality. So we do think of these sweet spots in terms of trade-offs where we can have high performance and we can also translate the technology to society in a very efficient manner.
Mm-hmm. What are the things you still wish you want to maybe design or engineer and still maybe we don't have the capacity to have it? Because you're still imagining that you want that, but still maybe we don't have the capacity to do maybe engineer certain, I don't know what you think about the future, or certain things that you want to have it already, but it's impossible.
Well, very few things are impossible. The only futures that are impossible are those futures that are a counter to physical law. So that allows for many, many futures to be achievable. I spent decades trying to translate technologies, trying to innovate and failing. And only fairly recently have I succeeded. So it really takes a comprehensive skill set to be able to translate technology. And it takes a lot of people. It takes a lot of creative individuals working together and working very, very hard for it to be possible. So a group of people with a shared vision is essential, with sufficient capital to make it happen.
Mm-hmm. Before going to the audience question, I have a question maybe about, because you mentioned failure and trial. how is your relationship with perseverance? Because I found this extraordinary when I see this kind of perseverance. How do you deal with that? What's the secret to having this persistence and perseverance to make something happen?
Yeah, if you study highly creative, highly innovative people and institutions, one discovers that they have certain characteristics. Being a force of nature is one characteristic, which means never ever give up. Believe in your visions so acutely that you just know it's possible and you refuse to stop until it's solved. Another characteristic is people that are highly innovative and creative. They don't have the language of failure. They have the language of exploration. So when something happens, if I build a bionic foot and I test it and it fails miserably, to me that's not failure, it's exploration. Because when something breaks, it doesn't perform as one expects. You're that much closer to solving the puzzle and achieving that high performance that you seek. So when I build a bionic limb and it performs in a way that is not consistent with the dream, I jump up and down with excitement. Where someone else may say, "Oh, I failed. I guess I'll give up." To me, when it doesn't perform, I'm that much closer to success. So it's exciting. It's an exploration. It's not failure. So that's another characteristic.
Wonderful. So maybe we can have a few questions from the audience. Do you expect generative biology a competitor for prosthetic technology in the long run?
Yeah, I'm not sure why the question's being asked, but a friend of mine is a synthetic biologist, and he says, "Hugh, why are you wasting time trying to build limbs out of synthetics? Why don't we figure out how to grow them back?" That's kind of an old-fashioned view, because very, very soon, for example, our synthetic artificial muscles will be far superior to biological muscle in terms of force generation and energy usage and whatnot. So, I don't view that the biological limb in its innate form is the best we can do. I think technology will become extraordinary, and therefore we should continue to think about this merging between electromechanics and tissues, because that ultimately in 50 years will result in the highest performance.
Mm-hmm. And also a question about why we can't have a tentacle-like leg that be flexible, ending and adapting to different environment. I think a question about having different morphology, like tentacle legs. Do you ever thought about that, having tentacle legs that be flexible, ending and adapt to different environment?
Yeah, I mean, there's all kinds of novel sensing strategies that one can envision and that are being actually pursued in laboratories across the world. And a lot of the sensing, artificial sensing, has biological counterparts, little hair cells, if you will, that are synthetic, that somewhat work like biological hair cells, would be an example. So, yeah, there's Bionics is a wonderful field to work in, because nature has provided us such a vast array of capabilities, just glorious and beautiful capabilities, and it's a tremendous fun to try to use engineering and design to emulate those capabilities.
How do you see maybe in academia the way it approaches a problem? Because you really try to make a difference to people's life. I think that's really phenomenal, and I have a huge respect for you for that. How do you see the equation between being academia and doing research, and at the same time doing something, realistically speaking, it's changing people's life? Do you see the overall research in academia, especially in robotics, going maybe in the right direction or investing or funding in the right direction? I don't know if you get my point.
Yeah, again, to not only expand human knowledge, but also to build devices that are translated to society is very challenging. And the key to success is diversity. You need an extraordinary intellectual diversity represented in your team. Again, the human body encompasses so many domains of chemical, mechanical, electrical, and so on. And you need that tremendous diversity represented in your team. And if you're translating, you also need designers and artists. You also need business minds as well. And you need a lot of capital. So the problem with some areas of academia is the laboratory perhaps doesn't have that diversity. And therefore, nothing from the laboratory is ever translated to society. Because inevitably a mistake will be made in the design, and it won't be a device that can be commercialized. Whether the mistake is a device that's too costly or doesn't fit or doesn't perform properly. Mistakes are often made when there's a limit on the diversity and the scope of intelligence of the full team.
I think maybe if someone interested to be studying biomechatronics or be in this field, do you think it has to have a huge depth knowledge and physiology? Because we already have physics background and mechanical engineering and biophysics. So do you think to understand the problem, because I think that if I understood correctly from the imputation already there's a problem, and your story, I think, very inspiring how you're pushing the boundaries of understanding and what is really can be done. So what does it take to be efficient and understand the problem?
Some labs are filled with incredible engineers, and some labs are filled with remarkable scientists of biology. And neither of those types of labs tend to be terribly successful. The scientists don't have the engineering sophistication, and the lab with engineers don't have the scientific sophistication. So the key is to have sophistication in both science and technology, purely from a device functionality perspective. But if you also want to translate, as I've emphasized in my last remarks, you also need experts in regulatory, clinical work, reimbursement, formation of companies, and so on. So again, often projects fail because an insufficient level of expertise exists at the beginning of the project. And then mistakes are made and the project just ends. So the key is to have many voices, many perspectives sitting around the table at the very beginning of the initiative.
I'm curious to ask you what makes you fulfilled, maybe in what you're doing, makes you fulfilled and be passionate to keep going what you're doing.
It's very powerful that I use prostheses myself, and on a few levels that's important. One is I intimately am aware of the consequence of poor design. I've spent my life trying to work with bad design, and I know firsthand how devastating and painful it is to trying to go about the world and you're surrounded by technology that's incredibly poor in its conception and design. So that's one aspect. Another aspect is I'm often the first human to test the technologies that are being conceived in my laboratory. I'm the first person to feel it, to experience it. because I can feel it and I also know the physics and engineering in my head, I can really quickly find the bug and solve the bug. Where another person may know the science and the engineering, but can't feel it, so doesn't come to the solution as quickly as I do. So that's an interesting advantage that I have. And regarding my passion, again, I know how painful it is to be in a world with design that doesn't work. And I know how extraordinary it is and life-changing it is to be given the gift of a fantastic design, whether it be a beautiful chair or a prosthesis or an exoskeleton. Great design leads to just absolute joy and human expression. So what really drives me and my passions and whatnot is the times in my life where I can put out into the world a fantastic design that improves people's lives.
Mm-hmm. Very beautiful. Maybe it's a question about the design and beautiful design, because you speak about the beauty, and for you every day when you imagine, because you mentioned as a kid you really was imagining the future, and I'm not sure if you still do that, but what kind of future do you think about? You want to change that drastically, the shape, whatever. I don't know what kind of crazy ideas you have.
I mean, in the short term, I would love to see a person with leg amputation dance ballet. I'd love to see a person with no arms play a Beethoven sonata at normal speeds, normal expressions. Longer term, I'd like to see a world where society doesn't have such a narrow view of human intelligence and human beauty, that we greatly expand human diversity and our notion of what's beautiful and what's intelligent greatly expands. Right now, society has a very narrow view of what a beautiful woman looks like and a beautiful man looks like. We have a very narrow view of what an intelligent person is. Imagine a world where I hope we will be 50 to 100 years from now, where humans can express all kinds of shapes and morphologies and dynamics, all forms of thinking and expressing and feeling. As we blend our physiologies in with the built environment, we will have this greater capacity to express. And my hope is that will expand human diversity, not shrink human diversity, and fundamentally change our view of beauty and expression.
Mm-hmm. Wonderful. Maybe that's a question. I'm curious about what life means to you, because I don't know the question, why I'm here, what I'm doing. And I don't know if there is something you would like to change, or in retrospect, when you look at something if I have opportunity, I would like to change it. I don't know if you have any thoughts on that, what life means to you.
I mean, I often say that I believe that we can, in this 21st century, solve disability. So right now, because of poor design, humans across the world experience disability. And my hope is, at the twilight years of this century, that our technology is so sophisticated that humans no longer experience disability. It's a human rights issue, as I see it. Today we live in a world where if you're not able to see, there's insufficient technology to allow you to see. If you're not able to hear the way you wish to hear, there's insufficient technology to allow that. If you're paralyzed and you want to dance, there's insufficient technology to allow that. So in the future, I hope we all have the human rights through advancements in technology to be able to to see, to hear, and to move, and to live a life without severe depression, for example, if we so choose. Today, that's hard to imagine because we're so used to a humanity that simply has to live with profound experiences of disability and limitation. It's hard to even imagine a society without that, but that is my dream.
Wonderful. It's such an honor. I have huge respect for you, but I don't know if you have any final words you'd like to say for robotics community or people listening. Any final words you'd like to say?
I mean, what excites me, sometimes we make the mistake of saying, oh, there's this certain cohort of people that are creative. And the rest of humanity, well, sorry, they just weren't born with the right genetics. I don't believe that. I think creativity is an emotional way of being that's largely cultural. And that's tremendously good news because as parents, we can teach our children. And as community leaders, we can teach our communities to be more creative and expressive, and to be part of the global effort to solve tremendous problems, whether it be in disability or the environment or politics. So I'll leave you with that thought.
Thanks so much for listening to this episode. I hope you really find it useful. And let me know what you think if I have to improve any parts of the future conversations or the way I do the podcast. I would be grateful to receive your feedback and your thoughts, how we can make it maybe better experiences. So thank you, and I hope you stay safe and healthy, and see you next one.